coming back to Oceans and Health. Today we have Dr. William Cheung from the University of British Columbia. Dr. Cheung studies the impact of climate change and fishing on marine ecosystems. He received his training in Hong Kong for the most part, I believe, and has been at UBC for several years, so an honorary Canadian.
Yeah, but I'm a Canadian actually.
Oh, factual Canadian. Good. So take it away.
Thank you. Thanks very much, and thank you very much for Elsie for inviting me to come to speak in the Oceans and Health seminars for this in the Center for the Environment. I really look forward to interacting with all of you and discuss about my research and other topics that are related to the oceans or the environment. And so my work, as people said, is in the last decades has focused a lot strongly on the effects of climate change on marine ecosystems and fisheries, and the ways that we can do to mitigate and adapt to those impacts. So the presentation today that I will talk about will focus us on some of the works that I've been doing in that line of research. Okay. And I'm sure you are all familiar with this, but just to highlight the importance of the oceans to biodiversity and our society. The oceans provide us with fish, so the fish that you have on your dinner tables from the oceans, very important. It holds a lot of biodiversity in the ocean, from bacteria up to marine mammals. It provides habitats for the species, and those habitats are also important to human well-being as well. And the food web actually provides functions to ecosystem services, as well as the oceans provide us with livelihood and other economic values. However, the oceans now is being affected by a variety of human drivers, both direct and indirect. And I'm sure you're familiar with all of these. Some of the highlights include overfishing, habitat destructions, coastal development, oil and gas explorations, pollution, and some of the works that, for example, Elsie has been working on to highlight those kind of potential impacts on ecosystems and human well-being. And we know that based on studies in the last few decades that another drivers of change in the ocean is through human-emitted carbon dioxide and other greenhouse gas to the atmosphere, which affects global climate. And as you know, the Earth's surface is warming up. So I pulled this up from a website called the Climate Interactive, which keep track of the current latest projections of the warmings under different scenarios of greenhouse gas emission, as well as keeping track of how much commitment each country have in terms of limiting their carbon dioxide and greenhouse gas emission. So basically, this is a thermometer that gives you the end of century Earth's surface temperature warming compared to pre-industrial level under different scenarios. So the yellow line represents the business as usual, strong high emission scenario. And it will give you a world of around 5.4 degrees Celsius warmer than the pre-industrial level. While the 3.5 degrees Celsius warmer is based on what we call the intended naturally determined contributions. So each countries, in last year, in the last couple of years, many countries have made voluntary commitment of how much carbon dioxide and greenhouse gas emissions they will do or they will limit in the future. And by summing up all those commitments from China, from USA, from other countries, and putting that into the climate models, they come up with a warming of around 3.5 degrees Celsius. Now, what is our goal? And as you know, under the United Nations Framework Convention on Climate Change, and particularly the meetings they have in Paris last year, they come up with a Paris Agreement that make a suggestion that the world should go to aim for a world with 1.5 to 2 degrees Celsius warmer world, which goes to here, the 2 degrees Celsius world. So you can see that the current commitment only allows you to drop a degree Celsius from the high emission scenario, while it is still quite far away from the Paris Agreement. So these are some of the key indicators of warming that I hope you make a mental note, because I will go back to these temperature references in my presentation later. But then to me, what I'm interested in is how does this warming will affect the ocean, and thus the organisms and surfaces that we extract from the oceans. And these are some of the projections for the key aspect of the biogeochemistry that climate modelers and oceanographers project in the next few decades. Basically, we will have a warmer ocean with increase in sea surface temperature. The red line represents the high emission scenario, while the the blue line represents the strong mitigations, low emission scenario. We call it the representative concentration pathway 2.6. So we will have much warmer oceans, around 3 degrees Celsius warmer than the 2000s level. We also have an increase in sea level. However, there will be a decrease in pH, which is a measure of acidity, because carbon dioxide, when they dissolve into the seawater, they will actually become more acidic and increase lower the pH of the seawater. And associated with that, with ocean acidification, is a decrease in the aragonite saturation state. Basically, it is a chemical measure of how difficult shellfish can make their shell. So the lower this saturation state, the more difficult the shellfish can make their shell. So this is an indication of the potential impacts of ocean acidification on marine shellfish. Besides that, there is also a projected decrease in oxygen content, particularly in some part of the oceans. And oxygen is one of the most important fundamental molecules for many marine organisms. And so its decrease will have a big impact on marine life. So we know that now that, okay, the ocean conditions will be changing because of climate change, and it actually is already changing. The next question is, what would it mean to the marine ecosystems and ecosystem services? How would it affect biodiversity and fisheries? This is a picture of a coral reef after a massive coral bleaching event, which is projected to become more frequent under climate change. In order to understand the consequences of climate change on marine ecosystem and fisheries, we need to use a multi-level approach. We cannot only study one level of organization. We need to have a more comprehensive understanding of responses and vulnerability of different level of organizations of the socio-ecological systems. We start off with, for example, the individual level. We want to understand how marine organisms, fish, shellfish, will respond to changes in ocean conditions, temperature, oxygen, salinity, pH, by changing their physiology, body size, reproduction, growth, and how would then affect the population dynamics, both spatially and temporally, and how all these changes would affect community structure and ecosystem dynamics, predator-prey interactions, and things like that. Also, we want to then understand how these biological change would affect the society through changes in economics, how changes in distributions of fish or productivity of fish would affect the profitability or the cost of fishing, and also the interactions with other global issues that are related to climate change. For example, change in the global food supply because of climate change, or changes in fuel price, or energy supply, and things like that. So we need to take a really comprehensive, holistic approach to understand the effects of global change on the oceans. And in my presentations, I will touch on some of my work that look at these different levels of organizations. We first of all talk about some of the evidence of how climate change actually affects the biology and the ecology of marine organisms. And secondly, I will talk about our works of linking the understanding of biological responses to climate change to informing how we can project future changes in biodiversity and fisheries under climate change. And then I will talk about the implications of all these changes for fisheries, for economics, as well as for management. And at the end, I will highlight some of the ongoing and future research and hope to discuss with you more about that after the presentation. in fact, in the last century, there were lots of biological work that tried to understand physiological responses of marine organisms to environmental change. Thermal biology is a really well-studied field in physiology. And so we have a good understanding of the physiological responses to things like temperature and oxygen. So this is the generally accepted framework of physiological responses to different changes in temperature. Marine organisms, particularly fish and invertebrates, they are cold-blooded endotherms. So their body temperature is affected by environmental temperature. And their body functions operate optimally at a particular range of temperature. And when temperature increase or decrease from that optimal, their body performance, growth performance will decrease. And at some point, the temperature will become too high or too low for them to survive, and they will die. And further stress, like reductions of pH or increase in carbon dioxide concentrations and reduction in oxygen levels in the water, actually reduce the scope for growth, potentially making the species more sensitive to temperature change. At the same time, we know that organisms are not the same biologically. They are adapted to the environment. So, for example, species that are adapted to the polar environment, they have much narrower temperature tolerance limits because they survive in an environment that have a quite stable temperature throughout the year, for example, in the Antarctic. Well, compared to species in the mid-latitude, in temperate region, there is large fluctuations, seasonal fluctuation in temperature. So those animals are adapted to survive in those environments with a much broader range of temperature tolerance. And tropical species tend to have an intermediate kind of temperature tolerance. And this kind of basic understanding helps us to allow us to make predictions of how different types of organisms and organisms in different environments will respond to environmental change. For example, ecological theories predict that aquatic ectotherms would distribute themselves to maximize their growth performance. So we know that then with temperature changes, it would have an implications of their ecologies and distribution. My work focuses a lot at a large scale, so global scale that include a lot of different species and ecosystems. One of the limitations of that is that often we have difficulties in getting really detailed physiological data because there's only a handful of species that we have good physiological work that has been done on those species. So we use some statistical modelings to actually infer the physiology and biology of the organisms. One of the things that we use a lot is to use the occurrence record of the animals. This is one of the most available biodiversity data that we have for the oceans. There's a global database noting where the species has been occurred geographically in the last century or so. So for example, this is for cod. We have data of knowing in which geographic locations cod has occurred in the last few decades. And then we can overlay that with environmental conditions, assuming that species currently are actually adapted to those environmental conditions. And then we can use various species distribution modeling approach to predict their environmental preference and thus to map out the distribution of the species. So this is an example, again, for cod in the Northeast Atlantic. This is the predicted distributions based on a model that infer the environmental preference of the species from the occurrence records and the observed environmental data. Red means higher relative abundance, predicted relative abundance, while blue means relatively lower predictive abundance. And we can do that for a lot of different species. And in this case, a lot of our work have a strong focus on fisheries, important species. So we look at all the exploited species, both fish and invertebrates in the world, around thousands of species. And then we can map out the mean environmental temperatures of their distributions, as well as the range of preferred temperature. So this is a proxy of the tolerance limit, of the thermal tolerance limit of the species, whether it has a wide tolerance limits or a very narrow tolerance limits. And this is basically a proxy of what kind of habitats the species occur. For example, in very hot environment, like the tropical environment, representing tropical species, they have a much narrower temperature tolerance limits. And so is polar species. relative compared to species in the intermediate range. So this kind of feedback agree with the theoretical understanding of the thermal biology of different species across different biomes. We can also use those kind of techniques to map out species richness around the world. So we predicted the distributions of 1,000 species of fish and invertebrates, and then we overlaid those maps together to get a sense of the distributions of species richness of the exploited species of the world. Red means high number of species, while blue means low number of species. And this really helped us to then look into the next questions, which is how species diversity as well as distribution and abundance would be affected by global change. If those underlying environmental factors changes, how would that affect species distribution? And the basic hypothesis is that imagine that this is the distribution range of a particular species along the depth and latitudinal gradient. And beside, the temperature is the gradient is represented by the color in the background. So with ocean warming, species will shift to high latitude regions or to deeper water. And there is considerable implications for conservation and fisheries. For example, if this species is a commercially important species, such shift in distribution will have large implications for resource sharing. So in this case, country A will gain, while country B will lose. It's actually happening. For example, I don't know whether you've heard about the Atlantic mackerel debate in the European waters, where mackerel is shifting the distributions from Western European countries to Northern European countries like Iceland, Faroe Islands. And those countries, Iceland, unilaterally increase their quota. That make a lot of the other European countries angry, because that means that they will be taking a bigger share of the mackerel stock. So these kind of things is predicted to happen more in the future. And we often measure the extent of such responses by looking at the distance that the distribution would shift under climate change over a certain time frame. So we measure the kilometer shift of distributions per decade. And using that kind of matrix, we can then look at historical record and see whether things are already changing. And in fact, it is already changing. So this is a study done by Polskanski colleagues. That is a large meta-analysis of published records of species distributions for a wide range of different species in the last century. And this is a measure of distribution change, kilometer per decade, towards high latitude region, or in direction that is expected under climate change or global warming. And so this is from benthic algae up to fish, and majority, almost all of the taxa have a positive shift in distributions in a direction that is in line with the hypothesis, except for the non-bony fish like sharks and rays. And the shift for fish is around 30 to 40 kilometers per decade. At the same time, we also want to see whether there are also evidence in those shifts in the fisheries catch, because actually the fisheries data is one of the most comprehensive coverage in terms of geographic coverage of the data, and it has a really complete time series too, from 1950 to now. So in this study, we hope to try to detect whether we can there is already signature of responses of fish species and fisheries to climate change. The hypothesis is that with ocean warming, we will be seeing more warmer water species denoted by the colored red and yellow fish in the fisheries catch from 1970s to now. While this is in the high latitude region, and in the tropics, basically the species that are slightly cooler water adapters will decrease in the catch. And we use an indicator called the mean temperature of the catch to measure or detect that changes. This is a fairly simple indicator. Based on our species distribution work, we can infer the preference temperature of each of the species that is represented in the fisheries landing. So in this case, for example, cod has a preferred temperature of 6 degrees Celsius and flatfish 10 degrees Celsius. And then we look at the mean preferred temperature of all the species in the catch in a year, weighted by their landings or catches. So in this case, over time, if the catch is increasingly dominated by warmer water species, the mean temperature of the catch will increase over time. So we did that for each large marine ecosystems from 1970 to now, all over the world. And basically, we find a strong, significant correlations between change in mean temperature of the catch and sea surface temperature, after accounting for the effects of fishing and other ocean variability. And this is a summary of the world. So this is the high latitude or temperate and high latitude ecosystem. The mean temperature of the catch is denoted by the red color, while the sea surface temperature is the gray color. So we find a consistent increase in mean temperature of the catch as sea surface temperature increase. But in the tropics, the pattern is slightly different. Mean temperature of the catch increase initially and then flat and then level off, although sea surface temperature continue to increase. We thought at first we were thinking why these patterns occurred, which is slightly different from what we expected. But then when we think deeper, it actually matched with our expectation because in the tropics, it's already the hottest part of the ocean. So there's no colder water or hotter water species migrating in the tropics. The species are there. There's only local extinction, so there's only species moving away from there. So this initially increased % species moving away from the tropics, while at the end, only species that can tolerate a higher temperature will continue to survive in those areas. And the changes vary between ecosystems. So we find that the data actually support our hypothesis of what we are going to see in the fisheries. The next question then is what would happen in the future? Will the change continue, or will there be a different patterns of change? In order to make projections of the future, we then resort into using computer simulation modeling work. So this is a basic framework of our modeling works to look at to develop projections of future change in biodiversity and fisheries. We start off with projections from global climate ocean models that provide us with how the ocean conditions will change, like temperature, oxygen, salinity in the future under different climate change scenarios. At the same time, using the occurrence record and the species distribution modeling work, we can infer the temperature preference, habitat preference, and based on global database, we get a good understanding on the biological characteristic of the species. And then we put it all into a fish models to make projections of future fish distributions and catches. This is a more detailed zoom-in framework of the fish models. I won't go into this in depth, but if you are interested, I'm very happy to go through this with you after my presentation. So basically, the ocean conditions that the fish models call the dynamic bioclimate envelope models account for include temperature, oxygen, acidity, sea ice, salinity, affections. That then affects the ecophysiology of the organisms, like growth, life history characteristics, body size, maturity. It will affect mortality of the fish and thus affects population dynamics. At the same time, these ocean conditions also affect the habitat stability of the environment. That also affects population dynamics. And the phytoplankton or primary productions in the ocean then through the food web affects the potential protection of the species. So this is an example illustrating the current distribution that I showed you earlier and the projected future distribution. This is using the business as usual scenario in 2050's time frame, so mid-century time frame. So this is a time lapse look of the change in distributions. There you notice a shift in the distributions towards high latitude regions, with species moving away from the North Seas. And we've done this kind of modeling for the 1,000 species that we look at or exploited species, and we can then map out the impacts on the change in species richness. So we use two indicators. The first indicator is the rate of species invasion. It is a measure of the number of species newly occurring in a particular location relative to its initial species richness. So it means that when a species moves to a novel or new habitat, then it will add to species invasion. On the other hand, when a species moves away totally from a particular habitat, it will lead to species local extinction. So in this case, as you may expect, there's a high rate of species invasions in high latitude regions such as the Arctic and the Southern Ocean, while there's also high rate of local extinction. In this case, it is along the tropical oceans because species are moving away from the tropics with increasing temperature. And this is even more clearer views of the rate of local extinction and invasions across different latitudes. So this is the measure of rate of invasions in blue color and local extinctions in red color. This is a latitudinal zonal averages. And the blue line represents the use of different structure of our fish model. So it represents some uncertainty measures of the projected rate of species invasion and local extinction. So clearly you see a large invasions in high latitude regions and local extinction in the tropics. And with the low emission scenarios, you can substantially reduce the average rate by almost half of what compared to the high emission scenarios in the 2050s time frame. Okay, so now the next question to us is, with all this shift in species distributions and patterns of biodiversity, how would it affect fisheries? To give you a basic understanding of the trajectory of global fisheries, this is the estimated global fisheries catches from 1950 to the 2000s period. This is based on the latest data from the catch reconstruction data published by my colleagues Daniel Pauly and Dirk Seeler in the CMRS project. So this is an improvement from the official Food and Agriculture Organization's landing statistics. While the green color here represent our last iterations of reconstructions of the global fishing effort over time. It's quite obvious that since the 1980s, global fisheries catch do not continue to increase, but stabilize or even decrease. Although fishing efforts continue to increase, which means that we are already reaching the maximum capacity of producing fish from the ocean, at least for the traditional fish stocks, assuming that we don't move into exploiting new fish resources. So it also means that there is a stronger role that changes in climate may play in affecting our fisheries production. Because in this case, we cannot catch more fish by fishing harder. And even actually, if we fish harder, the catch will continue to decrease because of overexploitation. So it also means that these fish stocks will be quite sensitive to environmental change. With changes in productivities of the fish stocks, it will actually have an impact of the amount of catch that we will get from the ocean. And we know that global primary production is going to change in the future. Primary production is like the grass and other plants on land. They are the main source of energy to power up the whole marine ecosystem and fish stocks. So changes in those net primary productions will also have a big consequences on high trophic level production. And this is the projected change in net primary production using the climate models, Earth system model that are used by the Intergovernmental Panel on Climate Change. Blue means decrease, while the red means an increase in net primary production. The dotted area represents area where there are good agreement between different climate models. So you can see that a large parts of the oceans will suffer from a decrease in net primary productions, particularly in the equatorial regions, Pacific, Indian Ocean, while the Arctic and some part of the Southern Ocean may increase. And overall, there will be around maybe 5 to 10% decrease in net primary productions by the end of the century under the high emission scenario. So in this case, we have some understanding of how net primary production would change. We know how species distribution would change. And we know a bit about about the trophic ecology of the species. We can then use these information to try to make projections of how fisheries catch would change in the future. The first step that we did was to look at existing data, catch data, and see whether there is a good relationship between net point production, species distributions, and trophic ecology. So we took our thousands of species and measure or estimate the maximum catch as an indicator of the productivity of the fish stocks in the world. And then we look at the relationship of the maximum catch with net point production, the trophic level of the animals, and distribution range of the animals. And we find a fairly strong relationship with that, explaining around 70% of the variance of the estimated productivity of the fish stocks. So it means that we can apply this kind of relationship together with our fish model to make projections of future fisheries production. And this is our new update of our projected change in catch from by 2050 relative to now under the high emission scenario, RCP 8.5. The red represent a decrease in catch potential of up to more than 30%, while blue is increased. So by 2050, there's a large part of the Pacific that will suffer from a large decrease in catch potential of over 30%, while only the high latitude regions such as the North Atlantic or North Pacific may gain from climate change. And there are quite substantial implications because these areas are also areas which have a strong dependency of fish catch. Some of the works that Chris did does actually showed the importance of fish catch to kind of the health of the peoples in there. And so this decrease in catch may even have a proportionally even larger impacts on those communities relying on fisheries. We can turn this into a biologically relevant climate impact indicators. So in this case, we look at the different level of atmospheric warming and how that correlates with different level of changes in maximum catch potential, so the potential fisheries catch, as well as species turnover. Species turnover is a sum of species invasion and local extinction. It means that the fisheries have to deal with all this swap of species that they are targeting. Cod fishermen may not be able to catch cod. They may have to catch some of the more warm water species in the future. So there's additional impacts that they have to deal with. What we find globally is that if we look at the catch changes, it scales linearly with global warming, while species turnover actually scales non-linearly. So this patch represents the Paris Agreement, the 1.5 to 2 degrees Celsius target. And compared to the index, so this is the committed emissions limitations that will generate this around 3.5 degrees Celsius warming. So there is a linear increase in benefits that we can get by meeting the Paris Agreement, while for species turnover, the benefits will be really substantial because there is a non-linear change in the impacts. After 2 degrees Celsius, impacts substantially increase. So this provides us with further justifications of doing much more to meet the Paris Agreement. And particularly for the tropical regions, the slope or the scaling is even bigger, and even for the maximum catch potential, the scaling between atmospheric warming and maximum catch potential is non-linear, meaning that there is a substantial decrease in maximum catch potential after the warming exceeds around 2 degrees Celsius. So this, again, from the perspective of tropical countries, is really give them a strong incentive to ask the world to do much more in mitigating carbon dioxide and greenhouse gas emission. Oops. Then we want to also speak to policymakers about our work, and one of the ways to do that is convert the impacts into something that they like to see, which is dollar. So, for example, in some of our work in collaboration with economists, we try to convert maximum catch potential into landed values by linking that to a global database of fish price. So this is a work led by my colleague Vicky Lamb, and what we projected is the change in the landed value in the oceans, in the countries. So on land, that's the projected change in landed value in each country, While in the ocean, that's the projected change in the catch potential, as I presented to you earlier. So the picture is pretty consistent with our story. In the countries, for example, in the Pacific or in the West Africa, they will suffer from a large decrease in potential landed values, the amount of revenues the fishermen can get by selling their fish, while only some of the high-latitude countries like Iceland, Greenland may gain from climate change. So far, I've focused a lot on looking at global warming, climate change, and the related change in the ocean conditions. But then there's another dimension of greenhouse gas emission of carbon dioxide that has gained a lot of attention in recent decades, which is ocean acidification. So that's a really certain changes that we know. It's basic chemistry. With carbon dioxide going into the water, it generates more hydrogen ion concentration, increased partial pressure of carbon dioxide. That would then have an impact on organisms. And this is a meta-analysis of published information of potential sensitivities and impacts of different carbon dioxide, partial pressure of carbon dioxide treatments to different types of organisms. And particularly, it finds that mollusks and warm water corals are most sensitive to ocean acidification compared to, say, crustacean. And this is the projected decrease in pH over time by the end of century relative to now. So the bluer the color, the lower is the pH that is projected to go. And you will notice that one of the hotspots of ocean acidification is in the Arctic. So we did a case study in the Arctic trying to look at the biological and socioeconomic consequences of ocean acidification there. We link our fish models into the economic impact model, and we make assumptions based on our best understanding of the biology at that time of how sensitive different organisms will be to ocean acidification. So for example, with basal metabolic rate, fish may increase by 15% under a doubling of hydrogen ion concentrations, while adult mortalities will increase for invertebrates by 25%. And then we'll put that into our fish models, simulate change in distribution, abundance, and catch, and then try to link it to the economic impact models and see how much impact ocean acidification will have on the Arctic. So in general, the Arctic will still gain from climate change, even with ocean acidification, because a lot of fish species will move into the Arctic. There will be increase in primary production. So there will be a projected around 32 to 38% increase in potential impacts, in this case, of jobs, number of jobs generated from fisheries. But ocean acidification, in this case, when we compare the scenario with ocean acidification and without ocean acidification, there will be around 7% decrease in the number of jobs, or around US dollars of 90 million that will be generated from fisheries or related economy in the Arctic. And in addition, we also started to look at some of the more of a non-monetary impacts of climate change on coastal communities. And this is a work that is led by my previous master's student, Lauren Wederdom. So she focused on the First Nations communities in the Pacific coast of Canada, the British Columbia. These different dots represent different First Nation communities along the British Columbian coast. And what she did is she identified species that are important culturally and for food for the First Nation communities in the regions, and then use our models to project how the catch of those species may change in the future and the climate change. There is a substantial impact, particularly for species that are very important for the First Nations culturally and for food, like salmon, herring. So we project a large decrease in their potential catch by 2050. And there's also spatial differences in terms of the level of impacts. At the mid-century timescale, the southern communities will have substantially higher impacts compared to the northern communities. And that generated a lot of interest from the First Nation communities because that's really, they think that those kind of information will be really useful for them to start thinking about how they can plan ahead and make sure that they can minimize or adapt to the changes that we predict to see in the next few decades. So I would like to spend the next 5 or 10 minutes to just go through some of the newest ongoing work that we have been doing, and maybe to generate some thoughts or suggestions from you on these directions. So far, from the start of our work in like 7 or 8 years ago to now, we continuously and increasingly addressing some of the key gaps and the challenges that we identified in understanding climate change impacts on marine ecosystem and fisheries. So, for example, we try to address from our initial works to now, we try to address the effects of additional drivers like acidification or deoxygenations, the effects on life history of the organisms like body size. We project a decrease in body size of fish over time. We try to incorporate the effects of trophic interactions. We look at kind of how uncertainty will play a part in our model projections and how that can turn into information that can be used by policymakers in turning that into a risk-based estimate. And then also we started more on doing some more downscale and regional analysis that will speak more to the policymakers. And more recently, we tried to look at potential evolutionary responses of marine organisms, like using quantitative genetic models, and see how that would moderate the impacts of climate change on biodiversity and fisheries. We have been looking at socioeconomic responses, cumulative impacts of multiple drivers, and both climate drivers as well as non-climate human drivers. For example, we've developing collaborations with LC in trying to incorporate the dimension of contaminants into the ecosystems. Also fishing, the multiple drivers of fishing and climate and how that may exacerbate the impacts. We expand our works on species that are not wild but then farmed. So we have a project that focus on looking at climate change impacts on global mariculture. And then we look at implications for conservation and management. So given all this change, how can we adapt or mitigate those changes? And a lot of those work fall under the umbrella of a program that I'm co-leading, which is called the Nervousness Program. It is a program that started in 2011 and funded solely by the Nippon Foundation in Japan. And our starting collaborations include 6 different collaborators, with USBBC being the lead institute. So include University of Cambridge, Princeton, Duke, Stockholm University, WCMC, and Utrecht, covering different aspects of the oceans. So these are interdisciplinary projects because our goal is to use both social and natural science approach to understand the future of the oceans so that we can actually develop management and conservation measures to adapt and mitigate those changes. There's also a strong capacity building components in our programs, both in training new scholars as well as communicating science to the public and policymakers. And we just have a new expansions of our program with additional funding from Nippon Foundations to actually expand our networks to 9 more institutes, including Harvard with LC leading the contaminant work. So we hope to address more comprehensively different drivers, direct and indirect, on the oceans. And one of the things that we started really pushing more is to develop the integrated assessment models for the global oceans. So this is a conceptual framework that we first developed when we started the project. This represents how the linkages of different components of the ocean's socio-ecological systems have, from the changes in biogeochemistry to marine ecosystems and to the human dimension, and how at the human dimensions the different policies, actors may affect the decision makings and thus feedback into trophic change, ecosystems and oceans biogeochemistry. And so far, if you look at the existing literature, there's really lack in this kind of integrated assessment models. There are quite a number of such models for the terrestrial sites, which is really useful for global scenario building work that inform, for example, policies such as conventional biological diversity or in assessing the sustainable development goals. So we think that this kind of modeling framework will be really useful, and that's one directions of work that we're pushing a lot in our recent work. And that links to, for example, the collaborations with Chris, the work that Chris and Sam Myers are leading on with funding from the Wellcome Trust that link the changes in the supply of fish or availability of fish and how that will affect human well-being, particularly in nutritional well-being of coastal communities. So we think that this kind of more integrated work will be the main directions that we are going in the next few years. And I want to sum up with more cover as a positive side of things. I've talked a lot about impacts, vulnerabilities of marine ecosystem and fisheries to climate change. But there are actually solutions that can help us to deal with those impacts. So this is a set of solutions that we identified in the paper published last year. We divide the solutions into 4 different types: mitigation, protection, adaptation, and repair. So mitigation is quite direct. It's addressing the source problem, the root cause, reducing or limiting carbon dioxide and greenhouse gas emission. We think that is important, and we have to do it anyway. Protect means that we can actually conserve and protect particular environments and biodiversity to help them to deal with some of the changes that we will see in the next few decades. Adapt is actually to use some of the response. We know that there are adaptive capacity in the ecosystem as well as for human society. So it is actually enhancing and allowing the systems to adapt to these changes through, for example, migrations, both human as well as the ecology and development of new infrastructure and things like that. And then repair. This, for example, the very good example is for coral reefs. We know that even if we can do well in limiting our emissions, coral reef will have a substantial impact in the next few decades. So what we are thinking is that we need to then, in the future, if we were to be able to do well in mitigation, then we may have some chance to repair coral reef after they are damaged. And there are lots of colleagues that there are some colleagues that are putting a lot of effort in looking at potential methods to repair, such as assisted migration of corals, for example, and things like that. However, one key point is that a lot of the availability of this solution space is dependent on how well we are doing with mitigation. If we were to be able to do well in mitigation, so for example, if we were to meet the Paris Agreement, then all of these solutions would become available. But if we were bad with that, if we were going with the business as usual scenario, or even just the current commitment, we will lose this potential solution pretty soon, meaning that if temperatures continue to go to the 4 degrees Celsius, there's nothing we can do with protection. Coral reef will die out, even if we set up marine protected areas. There's not much scope for adaptation because there's limitation and constraint for adaptation. We cannot adapt infinitely. Also, because we won't have any chance of recovering, so there's no chance of thinking about repair. So the key message is there are solutions that are available, but they really rely on how well we can actually allow our society to mitigate impacts from climate change. So I would like to thank all my colleagues, including my collaborators, with here just so the UBC teams in contributions to the work that I just showed. Obviously, it's not my single person work, but a collaborations of a big team of people. And thank you very much.
Yes. So you talk a lot about latitudinal shifts in
Yes.
species in response to global temperature, but what about changes in the zonal direction, maybe driven by differences in ocean basin depth or changes in ocean circulation that could affect water mass temperature? I mean, how much of an effect do those processes have, and how well are they represented in the models?
Yeah, so we also see an increase in depth distributions of the organism, particularly for the demersal fish, because it's like on land, species move to higher mountains to get cooler temperatures. In the ocean, they do the same. They shift into deeper water. So we, both in the empirical records of species distribution as well as from our models, we both detect a shift in distributions towards deeper water. And also, in some area, particularly in the more regional scale, the temperature gradients and the changes are not that simple. It's not only latitudinal. There are multiple directions. So in some cases, species shift according to what we call temperature velocity. So basically, it's the gradient of temperatures in that area. Some of the gradients may be actually southward or into eastward or westward. Yes.
Is it so easy for the species to move downwards in depth? Does the light have no effect on them? Because as soon as you go into the ocean,
Yes, obviously, yeah, very good point. So there's limits for species to shift because there's a strong relationship between protection in benthic protections and depth too. So at some point, ecologically, the species would not be able to survive at a certain depth because they don't have food. Also, that there's also some physiological limits that would limit the species to go further deeper. So there was some flexibility. So for example, in our model, we allow the species to shift, but then there's a limit for them to shift too. Yeah. Yes.
As you know, there are several strategies proposed to mitigate climate change, and they call it geoengineering. And one of the strategies is to, instead of sequestrating CO2 from the atmosphere, and it is suggested to spray aerosols in the atmosphere, in the atmosphere to keep the sea surface temperature from increasing.
Yeah.
So would you please comment on this kind of geoengineering on the fishery or the trade-off between temperature and the CO2?
Yes. It's very good questions because geoengineering is something that people are thinking of in mitigating climate change. And for example, in the IPCC report, in Chapter 6 that I'm involved in, we did an assessment on the potential implications of geoengineering. What we find is that the effectiveness of geoengineering is really uncertain. So there's no single geoengineering methods that are proven to be able to scale up and be effective. And then the impact is really uncertain. We don't really know a lot about the potential impacts of having the geoengineering approach to the ocean. For example, in one approach, they say and also it doesn't address the other part of the impacts of CO2, which is ocean acidification. So, for example, a lot of it is because geoengineering is by reduction in solar radiation by increasing the cloud cover and things like that. Those kind of things do not reduce carbon dioxide concentration in the atmosphere, so it doesn't reduce impacts of ocean acidification. So it doesn't really address that kind of impacts. And so I would think that is a thing that people continue to explore, but I don't think it is a solution that is realistic enough that we should kind of put that in like a intermediate time step. Yeah. Yeah.
So I was really struck by one of the earlier figures that showed kind of the differences between types of organisms and the extent of their shift in range.
Yes.
You just see phytoplankton, zooplankton going way up there. So building off of that, so a lot of your species productivity for the fish was considering kind of phytoplankton productivity, but how is shift in the range of phytoplankton also coming into play into your models for shift in fish distribution? Do you think that's their shift is driving it more than their temperature, physiological, what they can handle?
Yeah. So right now, I think is a interesting question and important questions on the ecologies and what is actually driving changes in the fish stocks and ecosystems. It's always whether it's food or environment. So our hypothesis is that with the changes in the distribution of fish stocks, temperature and in addition, oxygen will be the key drivers. And primary production is a moderating effect. So it affects, for example, whether a habitat will be suitable for them because whether there are food available or whether how much of the production will there be when they shift into that particular habitat. So the first order effects is through temperature and oxygen because that really affects directly the physiology and the survival. And then primary production change then moderate the productivity.
Yeah, in that case, I think the Arctic is really interesting because you're going to have seasonality and light is so important up there. It's not just temperature that's modulating productivity.
Yes, yeah. Because, and the projected increase in productivity over there is partly driven by the increase in irradiation because of the loss of sea ice. You got more sunlight into the water, so it increased pine production.